It is now.
Hello, everyone. Welcome to the first seminar in 2024. Before we start, I would like to announce the fact that we will have a workshop for junior researchers that will take place on April 18. So please check our website on details how to submit the paper. And today we have the great pleasure to have Almut Veraart from Imperial College London as guest speaker, and Orimar Sauri from Aalborg University as guest panelist. If you have any questions during Almut's talk, please feel free to unmute and ask your questions. Or if you prefer, you can write them in the chat. Almut, the floor is yours.
Thank you very much, Adriana. So first of all, I would like to thank the organizers for the kind invitation. It's a great pleasure to present here. And I also would like to thank Orimar to join here. So this is joint work with Orimar Sauri from Aalborg University. So very happy that Orimar is here as well. And this is on non-parametric estimation of Trawl processes, theory and applications. And so this is ongoing work. We are actually currently revising the paper. So comments, suggestions are most welcome. Okay, feel free if you have a clarifying question or so to just interrupt me. Otherwise, I'll be more than happy to answer questions after the talk as well. Okay, yeah. So let's get started. So the motivation. Oh, we have a bit of a freeze. It's always when you try before. Now it's frozen. Let's see. Oh, it's not moving anymore. One second. I might need to stop share. Maybe it was I will just try again now because maybe the recording stopped this. 1 second. Okay. It's coming up. No. Okay, I'm not sure what changed this now. Just give me a sec. Ah, yeah, now it has moved, right? Can you see the next slide? Yeah, yes. Perfect. Okay, sorry about the delay. There was a bit of a delay here. Okay, so the motivation for this project was to look originally at a time series of counts, and count data arise in many applications. So we have applications in epidemiology, in medical science, in meteorology, network modeling, actuarial science, econometrics, and finance, and there have been lots of kind of works on modeling time series of counts. And in that context, the class of so-called integer value Trawl processes was introduced. And this is almost now, it's actually 10 years ago, this first paper on the integer value Trawl processes was published. And this was based on joint work with Ole Bandorf-Nielsen, Neil Shepard, and Asker Lunde. And this paper introduced univariate integer value Trawl processes. And shortly afterwards, I looked at some extensions in the multivariate case as well. And then since there has been a lot of interest in Trawl processes and related processes, they fall into a bigger framework, which we call Ambit processes and Ambit fields. But I'm not going to talk about these Ambit fields, but they are very special in class. and they are actually quite flexible in terms of for models. And then many people have looked into, estimation and inference problems in the context of these Trawl processes, also formulated in either continuous or discrete time. And originally we were just looking at essentially parametric estimation theory for such processes. And then with Orimar, we were thinking it would be actually very interesting to also explore non-parametric estimation theory for these processes. And then we said, okay, so let's try whether we can do some non-parametric estimation of Trawl processes. And I will obviously later define what these processes are. But I just wanted to tell you first what the goal is. So the goal is to develop a non-parametric estimation theory for what we will later call the Trawl function of these Trawl processes. And as a little illustration of this method, we wanted to look into non-parametric forecasting of Trawl processes. So originally, when we first looked at these processes, we had these integer valued count time series essentially in mind. But the class is much broader. The class is not restricted to integer valued processes. They cover real valued processes as well. So what I'm going to present today is essentially the general theory for also real-valued Trawl processes and how we can estimate the key Trawl function non-parametrically. And this is the estimation theory is based on an asymptotic theory. And then obviously, if you want to apply that in practice, you always have to ask the question whether that methodology actually works well in finite samples. So we then also tested the new methodology in extended simulation studies to get a bit of a feeling, you know, what kind of sample size do we need, what kind of interval width do we need so that the method works. And it seems to work fairly well in our finite sample studies. And then we also looked at an empirical application, and I will show you this at the end of the talk. So as I said, we have a first version of the paper from now actually a couple of years ago. It's on arXiv if anybody wanted to have a look. We also collected the code in an R package, which is called Ambit, because Ambit processes is the wider class, which contains the Trawl processes as a special case. And we also have the code for the empirical study on GitHub if anybody wanted to look at this. And also the data set we have used is also on GitHub. Okay, so the aim is now to do the non-parametric estimation of Trawl processes and then to illustrate the methodology in a financial application. So as I mentioned already before, there's a huge literature on modeling time series of counts, and obviously, I mean, this is a time series seminar, so many of you are probably quite familiar with the literature. And I mean, from my perspective, it seems a bit like that kind of in particular, the work on the count data goes a little bit in waves. So there are periods where there's a lot of interest in this count time series, and then, you know, there's a bit less. And currently there's again quite a bit of activity where people look into a count time series. So there are, I would say, I mean, there are quite a few different modeling approaches around, in particular in the discrete time series literature. I think two very prominent examples are the ones I'm listing here. So there's the class of discrete autoregressive moving average processes, and they were introduced in the late 70s by Jacobs and Lewis. And then as a kind of competing class, I would say, is the class of integer valued AR or AMA models. And they go back to the very influential work by Stoitel and van Haan. And this kind of approach is based on the idea of thinning. So you have essentially pretty much a classical AR or AMA representation, but rather than having essentially a multiplicative factor in as the parameter, you do some essentially thinning operation here. And so these are, I would say, two classes which are very widely used in applications. And then in addition, there are all sorts of regression type models, state space models, and also then various Bayesian approaches to modeling time series of counts and obviously other general time series. In our framework, when we are talking about Trawl processes, as I said, we started off by using this idea of trawling, and this is really the fishing net idea, which I will illustrate in a second, where we wanted to use essentially the idea which Stoitel and van Haan had in their work of essentially having some thinning. So we will be using some kind of thinning operations to construct our Trawl processes in an integer value framework, and then this can be essentially generalized to a real valued framework. And I mean, the literature on modeling time series of counts is obviously, as I said, is huge, and there's no way I can review it here properly. But I wanted to at least give you, you know, some indication of the related literature on the Trawls, okay? Because the Trawls have been around now for also, yeah, a bit over 10 years, I would say. And the first paper which mentioned the Trawl processes is by Ole Barnhof-Nielsen from 2011. And he looked at stationary, infinitely divisible stochastic processes. And he mentioned the class of Trawl processes as a particular important example. And but what turns out then is that there was actually earlier related work by Wolpert and Brown and Wolpert and Taku. They didn't talk about Trawl processes, so this is really the term which was introduced by Ole Barnhof-Nielsen. But Wolpert and Brown, Wolpert and Taku essentially studied a similar concept, but they talked about higher geometric figures moving in a higher dimensional space and so on. And kind of philosophically, this is exactly the same concept as the Trawl processes. So they have been around essentially for some time. And then when we first looked at these kind of processes, as I mentioned before, people were looking at parametric estimation methods, in particular, generalized method of moments and likelihood-based inference. So I listed some of the papers already before. I see Mikkel is here, I think, as well. So Mikkel has worked on the parametric estimation theory for the integer value Trawl processes as well. And so this is essentially the continuous time work. But then there's also a group around Paul Ducan and others who introduced the class of discrete time Trawl processes. And they then introduced the estimation theory, and in particular, actually asymptotic theory for discrete time Trawl processes. So there's quite a bit around now in this context in terms of theory. Okay, and then because the class is so flexible, I hope I will be able to convince you. So then we have used Trawl processes also in hierarchical models for extremes. So they have different kind of applications, so they can be used also in an extreme context. And I'm just listing a couple of papers here. And then I have the topic of the limit theorems. And as I said, so there was quite some interest in studying the limit behavior of Trawl processes, both in continuous and in discrete time. And as you see, there are various kind of sorry. Okay, so there's quite some interest in Trawl processes at the moment, and essentially our paper, follows up on this, because this is a very flexible class of processes. So I want to now obviously give you the proper definition of what a Trawl process is, but first of all, I would like to give you this kind of informal definition. So when you Google and ask Google what trawling is, then you will end up possibly on the Wikipedia webpage, which says that a trawling is a method of fishing that involves pulling a fishing net through the water behind one or more boats, and the net that is used for trawling is called a trawl. Okay, and so now think about the aim that we want to initially model time series of counts. Okay, so for example, number of people who are sick in a pandemic, or maybe we need some smaller numbers, but essentially something you want to count. Okay, and the way is, how can we construct a stochastic process which does the counting essentially for you? And what Ole Barnhof-Nielsen, when he introduced that class, what he kind of had in mind was this idea of this kind of fishing boat. Okay, so that you have a fishing boat moving along here on the ocean, okay, and we think of when the boat moves along in this direction, that this is essentially the time axis, that you then have essentially a spatial domain, which is the ocean. In our case, it's the depth of the ocean, okay, and then you have essentially fish in the ocean, and you catch the fish. Okay, so what you do is the boat is traveling this way. It pulls this trawl, the fishing net, behind it. And then because you catch the fish, you will then just count how many fish you actually have in the net. So at this point in time, you see on this picture, we have 4 fish in the net. So we would say the value of the process at this point in time is 4. Okay. And then you will see when the boat moves on, very soon that next fish will actually be caught. Okay. And then the process will go up from 4 to 5. Okay. So this is essentially how the values will increase, by essentially catching more fish. But we want to also have a process where, the values can decrease again. So in this construction, and this is where things don't align that well with the original fishing picture anymore, we will actually let our fish escape, okay? If the fish reaches the boundary of the net, we let them escape from the net. And so when the fish drops out, then the process goes down by 1 fish, essentially, okay? And that's where this kind of where the term trawl process comes from. Okay, so that we kind of have in mind that we're essentially catching fish, or we're doing some counting. Okay, so this is kind of where the name comes from. But obviously, this is not a mathematical definition. So I would like to make this slightly more rigorous. Let me see. There's a bit of a delay here. Just wait until this flips. while we wait for this to flip. So obviously when we want to make this kind of more rigorous, then kind of the natural way to keep in mind is that we can work with Poisson random measures, okay? So that we have some point measures which essentially generate points in space-time, so they will generate our fish, and we want to be able to catch the fish. Let me see, but this is still not moving. Okay. Sorry, I'm not sure why this is stopping again. Okay, I might just stop this share. I stop share maybe briefly and just start again. At least that fixed the problem before. Sorry about this. We just stop share. Okay, so we are back. Let's see. No, so it's still blocking this.
Maybe if you stop sharing and you move the next page.
Yeah. Okay.
Share with
Thank
that.
you. Yeah. Thank you. Yeah, I'll do that. Yeah. Okay. So let's just try again. Okay, so so now we're on the next page. Yeah, now I can flip things again. Okay, so this is now the formal definition. So we had so please keep that picture of the fish and the fishing net in mind. Okay, so we just want to formalize this now. So we will need some randomness. Okay, so we introduce our noise. The noise we will be using is what we call a Levy basis. So those of you have seen Levy processes before, so just keep that in mind. It's something very related. So what is this Levy basis? So we assume that L, if we want to model integers, then we say it's an integer valued Levy basis. Otherwise, it's just a Levy basis. We also want this to be homogeneous, so there's some kind of technical assumptions in the background. So what is a Levy basis? It's an independently scattered random measure which is infinitely divisible, and that means that we have a very nice representation for its cumulant function. So if I want to compute the characteristic function here, so I'm looking at the characteristic function of L evaluated over a set A, where A is a bounded Borel set in R2. So if I compute that, then this gives me the characteristic function. And if I take the distinguished logarithm of this, then I get what we call the cumulant function. And it turns out that for such a Levy basis, we have a very nice representation. So we get that this cumulant function factorizes into the Lebesgue measure of A. So you just get essentially the size of that set A times psi of z. And psi of z, you see here, is just the cumulant function, which you would know from, say, from a Levy process. So this is just the representation of the cumulant function of an infinitely divisible random variable. So there is, the first term represents a drift term, second term represents the part coming from the Gaussian part, and then we have essentially the jump part appearing. And so this is essentially a classical Levy-Kinshin representation. And the terms which are in blue are the ones which you would need to remove if you wanted to have an integer valued Levy basis. Okay, so if it's purely just integer valued, then you just have this this jump term here without the compensation, because you wouldn't need to compensate the small jumps here. You're essentially dealing with a compound Poisson process here. And otherwise, if you wanted to have a Gaussian part in there, then you have an additional part or possibly a drift part. So we can allow for this general kind of Levy setting. Okay, so this is the noise term, but kind of in your mind, keep in mind, this is essentially a Levy process kind of extended to an R2 setting, okay? And then in addition, we need that Trawl set, the fishing net, and we call this AT. So this is now the set at time t, and it's defined as an original, at first as a set A. So when I just write A, it's just the set at time 0. And if I want the set at time t, I would just translate it. So we are translating it in time t. So I give you first the definition of what that A is. So the A is the set, the fishing net. So keep that picture in mind. We have seen before. So this is the fishing net at time 0. So it's a subset of R2, where the first component is the time component. Okay, so we are looking at time 0 now. So we say everything which matters for the process at time 0 is in the past. Okay, so the time component can go from -infinity up to 0. Okay, because that's the current time we're looking at. And then we have to place now our fish. Okay, we have to place the points essentially in the ocean, in the two-dimensional ocean, and that's where the second component, the y, comes in. So we say that this y is bounded between this the time axis and the Trawl function. Okay, so A is what we will call the Trawl function. I'll give you a picture in a second, and so this is the set at time 0, and then if we want it at time t, we just translate it in time. And the important thing here is the Trawl process we want to construct. We want this to be a stationary process, so we will not vary the shape of that trawl. Okay, so the fishing net always has the same shape. We just pull it along in time. Okay, so this is the idea. And then when we define the Trawl process, we go up here to the first line again. So xt is now the Trawl process, and it's defined as this Levy basis evaluated over the set at. And this is defined as the stochastic integral, where you're integrating an indicator function over that Trawl set with respect to the Levy basis. Okay. And when you look at there are these two variables entering the x, this is essentially the spatial location of our fish, and the s, the time component. And when you see it's s minus t, so we depend on time only through that kind of difference, and that later ensures that we get our stationary process. Okay, and so actually when you look at this definition, you see this is what we would call a mixed moving average process. So the Trawl process is a very special case of a mixed moving average process, where the kernel function is just given by an indicator function. Okay, and as such it inherits all the nice properties of mixed moving average processes. Okay, so this is just to give you the broader picture. Also, the Trawl processes are very, we would call them almost universal, in the sense that for any infinitely divisible marginal distribution and for any differentiable covariance function that is non-decreasing and non-increasing and convex, we can find a Trawl process, or we can construct a Trawl process which has that marginal law and that given covariance function. Okay, so it's actually a very flexible class of processes to work with. And now, so this is the definition. Obviously, if you have a question about the definition, feel free to just, ask now or ask later. But this is the formal definition. Okay, it's a mixed moving average process where we are integrating essentially that indicator with a fishing net inside with respect to the Levy noise, and the fishing net itself will just be translated in time. And now the goal, okay, the objective is to estimate that function A. Okay, so the function A is essentially the boundary of the fishing net, and our objective is to estimate that function. And I want to illustrate now a little bit in this picture what's going on. So this is an example here in the first picture. We just see essentially a realization of a Poisson-Levy basis. So you see all these black dots, they all have the same size, essentially. If I were to project, so the black dots are the fish, okay, but in a kind of more formal way now, because they are generated by our Poisson random measure. So if I were to project the black dots down to the time axis, I would just get the arrival times of a regular Poisson process, okay, as you know it. So nothing fancy, okay, it's really just a Poisson process. We have the arrival times of the Poisson process, and then we have the dots here uniformly distributed on 0, 1. And then the turquoise shape here, so this is the fishing net, that's the trawl, okay? So this is the trawl set at a particular point in time, and you see it has this boundary, and this is the function, the trawl function we want to estimate. And the shape of that trawl function will determine the autocorrelation function of the trawl. Okay, so this is what our object of interest, essentially. And in this picture, I mean, I mentioned to you, we have to essentially count dots. So if I count the dots here, you see I have 2 black dots in the turquoise fishing net. If I go down in the second picture, you see a realization of that process. So this is the sample path of the Trawl process. And you see at this level, it's level 2, okay, because we have 2 dots in the fishing net. And then I'm essentially pulling that fishing net along. Okay, I'm pulling it forward in time. And then here, for example, we see we have 1, 2, 3, 4 dots inside, and the 5th dot is about to enter. Okay, and you see when I go down now, I see that the value of the trawl process at this point in time is 4. It's about to go up to 5 now. Okay, so this is essentially, just an illustration of the definition. But now you might say, well, that's still very simplistic, right? Because if I have this Poisson example, the process can actually only go up by 1 and down by 1. So that might work for some applications, but for many it's too simplistic. And then we can introduce the idea of having big fish and small fish. Okay, so we still have our dots here, but you see that the dots are of different sizes now. And so essentially we are going from a point process to a marked point process. So you can think that every dot has a mark, essentially a jump size associated with them on the size of the fish. And now you're collecting big fish and small fish. And what you need to do is, so again, we have the same fishing net, essentially the same trawl, and you have to now not just count the points, but you have to count essentially the marks, okay? You have to count the sizes of the fish. So I might have a fish of size 2, +2, +2, then maybe a +3. I have a fat fish coming here of size, 10 or something like that. So you have to essentially add up these marks, and then you get a bigger variety, okay? So then you get kind of much general count distributions here using general, essentially compound Poisson processes with jump sizes distributed on the natural numbers. Okay, so, and you see down here is again the path of the corresponding sample parts of the process. Okay. So now I want to show you how we can actually construct our estimator. So the process is a continuous time process, but it's very rare that you would observe such continuous time processes really continuously. So we put ourselves in the position that we say, okay, let's assume we observe this process discretely on an equidistant grid. So for now, we looked at an equidistant grid. I mean, that could potentially be relaxed, but let's assume this is the case for now. And again, the objective is to estimate the trawl function, so the upper boundary of the fishing net, okay? And so what we can show is that the process X, as it's defined, is a strictly stationary process by definition. And we also assume now that L, the Levy noise, is square integrable so that we can actually compute second moments. And if you compute now the autocovariance function, which we denote by gamma, so the covariance of xt and xt plus h has a very nice expression. It's given by the variance of L prime. So this is this kind of Levy seed which we associate with the Levy basis. This was this, infinitely divisible random variable we saw on the previous slide, which had this nice Levy-Kinchian representation. And this is multiplied now to the integral of that trawl function. And we integrate the trawl function here from the absolute value of h up to infinity. And so this is now... Yes.
Sorry, Almut. So maybe I missed this. So what's the process of the fish here?
So this is in the let me maybe just briefly go back. So the fish are generated by that Levy noise L.
Right. Okay. So that's
so this is in the discrete case, it would be essentially a compound Poisson process. Okay.
I see.
The background, which gives you the fish and the location of the fish and the size of the fish. Okay. And then we had this, Levy-Kinchian representation, which I had here. And this is where this kind of L prime term comes in. L prime is the random variable which has that Levy-Kinchian representation. Okay.
So
yes,
that's so. I'm just trying to imagine the situation where the fish escapes, right? From so how is that? Is it depending on the jump or?
Yeah. So okay, so it will depend. You see, it depends. So you might ask for how long does it stay in? In this realization, it depends on where it enters, right? If the fish enters high up here, then it will actually leave quite soon again. Whereas if it enters down here, it stays in for a longer time. But because of this Poisson assumption in the background, we have essentially a uniform distribution on 0, 1. So you have a kind of the same probability of ending up anywhere here. And then the minute, you're reaching the boundary, the process drops by whatever the mark of that fish was, essentially.
So they can escape from the boundary, right?
Exactly, only from the
Okay.
boundary.
All right.
Exactly.
Okay.
And because we have this assumption, I didn't stress that much, but we have the assumption that we are working with a monotonic Trawl function. So the minute they have escaped, they are out. Whereas if you were to, allow for some sort of bumps or so, they could potentially rejoin, but we're not considering that situation, essentially. So we are looking at a monotonic Trawl function here. And so they join at some point, when that line essentially hits the point, right? So this is when they join, and then depends on, how low they were essentially in that fishing net. They entered at a very low level, they would stay in the longest. But the memory of the time series will be determined by this decay, and I'll show you the formula now. This the Trawl function, there's a one-to-one correspondence with the covariance function, and I'll show you this now, and that's essentially what's in the background when we are constructing the estimator. Does that answer your question somehow?
Yeah, so just, I'm still a bit confused with the accumulation, because how to accumulate the fish.
So we're
Well,
counting.
it depends, I guess it depends on the process, living process, how. You
Yes.
see my, or just
So think of it as a compound
fish, keeping the fish inside, right?
Yes.
Uh,
So you see, so if I didn't have the Trawl function coming down, if I just kept all the points and move forward, then that would just be a Poisson process, as you know it. Okay, so the classical Poisson process, nothing fancy, but because we let them escape, so that's why we are not just counting upwards, but the level can actually drop again. So
Okay.
that's in some sense the difference between a pure Poisson, compound Poisson process and the Trawl process.
Okay.
But
And
they
now
have-
you are looking at the correlation in the number.
Exactly.
How much you capture? Okay, that's
Exactly. So this is
where you are interested.
exactly. So this is now obviously in time series always one of the objectives, right? To understand the autocorrelation essentially.
Sure,
And this
sure.
is what we use now. So it turns out that the autocorrelation or autocovariance function here is essentially determined by the integral over that Trawl function. And that also shows you actually that you get an exponentially decaying autocorrelation function, if and only if you're dealing with the exponential Trawl function. And for any other settings, the Trawl function and the autocorrelation will not be identical. But obviously, there's a close link through this formula. Okay. And now what we see is because we have this product, I have the product of the variance of this Levy term times this integral of the Trawl function. So in order to ensure identifiability, we need to now make some restrictions. So you can either say that if you're integrating that integral from 0 to infinity, you fix that, or you fix the variance. So we decided for now to fix the variance. We say the variance of that Levy noise is equal to 1. That doesn't mean that the process has variance 1, right? So the process can still have any variance because it comes from the product, but we are making an identifiability
And you are after A.
We are after A, exactly. We want to estimate A, exactly. And now you see, because of this nice formula, then you just do fundamental theorem of calculus. And if I differentiate my covariance function, I essentially get the Trawl function. Okay, so this is the main insight from the property of the Trawl process. And so now the construction of the estimator is exactly that, okay, because we see that the derivative of the autocovariance function gives me essentially minus the Trawl function. The idea is to just say, well, take the empirical derivative, okay? We take the difference of the covariance function on 2 legs, and we divide by something small, delta n, okay? And we hope that this gives us the right estimator. And the gamma hat, these are just the empirical autocovariance functions. And it turns out that this works, okay? So the main task was then, to prove, right? To prove that this is doing the job, essentially. And what I wanted to stress here as well, so this estimator, you see, we have essentially an estimator for all these different points in time t, where it essentially looks a bit like a step function, the way how we kind of approximate this Trawl function. You can use this estimator for any time t, but we propose that if you're after A0, that you use a slightly adjusted version of the estimator, which we show works better in finite samples, and also depending on what kind of Levy noise you actually have. So this would be our recommendation to use that in general, but the other one would also typically work. Okay. Okay. Are there any questions maybe about the definition? So the main insight for now is we observe that the autocovariance function of the Trawl process is essentially a factor times the integral of the Trawl function. And then by differentiating the covariance function, we get essentially the Trawl function back. And then we just take the empirical counterpart of this as our estimator for the Trawl function. So that's now the main idea.
Wait, just a question. Are you making assumptions about continuity of the Trawl function?
Yes,
or?
yeah. I didn't. I'm actually not mentioning all the assumptions here, but yeah, and also the monotonicity, which I haven't stated explicitly. Yeah, no, that's our underlying assumption. Yeah, thank you. Okay, I'm stating some assumptions, but not all of them. But if you're curious, please do take a look at the preprint on arXiv. So we first we wanted to prove consistency of the estimator. So we assume that the number of observations goes to infinity, and then delta n, this is the grid over which the width essentially of the grid over which we have our observations. This we assume that the width of the grid goes to 0. And then n times delta n, this is essentially the last point, right, where we have the observation, we send that to infinity as well. So if we have these assumptions, and then we have this kind of identifiability assumption that the variance of that Levy term is 1, and we also have a fourth moment assumption, then we get that our proposed estimator of the Trawl function is a consistent estimator of the Trawl function. And this is now pointwise for each t. Okay, so we get the consistency, and then obviously when we have the consistency, we typically ask, do we get some sort of central limit theorem as well? And it turns out yes. So and for the central limit theorem, we need more assumptions. So I wanted to skip some of the technical assumptions. So there are some technical assumptions in the background which we have listed in the paper. And we need an additional quantity. So we had already some assumptions on, how n delta n essentially behave together. There's an extra term now appearing in the central limit theorem. So we are looking at this limit of n times delta n to the power 3. And we call the limit of this quantity mu, okay? And now, depending on what that limit mu is, we get different limit results, okay? And so the 3 cases we have to distinguish is the case whether mu is equal to 0, whether mu is strictly between 0 and infinity, or whether mu is equal to infinity. And I would say the nicest case is probably when mu is equal to 0, because then we get essentially a classical central limit theorem. So we see that if we are looking at the difference between our estimated Trawl function and the true Trawl function, we have to scale it appropriately with square root n times delta n. Then we get that in distribution, this converges to a normal distribution where we have an asymptotic variance, which we can compute explicitly. So the asymptotic variance depends here, the C4, this is essentially the 4th cumulant of the Levy seed, which is, the noise which produces the fish. And then we have an extra term here where you see that integrals of powers of the Trawl function enter again, okay? So this is the first case when mu is equal to 0. And yeah, personally, I think it's the nicest case. When mu is bigger than 0 but strictly smaller than infinity, we see that we need a slightly different centering term. So there is now essentially an approximation error coming in, because we're essentially approximating our Trawl function via an integral of the Trawl function. So we make some slight adjustments to the centering here in the limit theorem. But then again, we get that in the limit, we get a normal limit with the same asymptotic variance, but there's an additional term. So there's an asymptotic bias term appearing. And you see this bias term has now the derivative of the Trawl function featuring, and this mu term, okay, square root of mu. And so that's also intuitively shows you if mu is equal to 0, then this term essentially isn't there, okay? So this appears if that limit mu is greater than 0. And then the not so great case, when mu is equal to infinity, you get essentially a limit in probability again to the derivative of the Trawl function times 1 over 2. So these are essentially the 3 scenarios we are dealing with in the context of when we want to construct a central limit theorem for our Trawl processes. So these, if you wanted to use them for estimation, then you see that these are for now still what we would call infeasible results, right? Because this asymptotic variance is not yet known to us. But similarly, when you obviously look at the functional form and you know that we have already estimated A, using our estimator for A, we can then construct essentially estimators for the asymptotic variance and also actually for the asymptotic bias. And this is what we are doing essentially in practice. So we can now replace essentially the asymptotic variance by its consistent estimator, where we literally replace these integrals by corresponding Riemann sums, where we use our Trawl function estimate. And then we get, a nice, what we would call a feasible limit theory, where we get essentially a standard normal random variable in the limit. And we distinguish again between the two cases, whether mu is equal to 0 or mu is strictly between 0 and infinity, because we need to do a slightly different centering here. So it's either AT, or we have this different term here again through this approximation error appearing through an integral approximation. And what we then, because this is now a feasible central limit theorem, so this is something we can test in simulations, and we have tested it a lot, and it worked quite well actually in simulation studies. So we could estimate the Trawl function very precisely in our finite sample studies. For the central limit theorem, when we are comparing with the Gaussianity, there obviously we have these assumptions that n has to be big, delta n has to be small, and so on, and they have to have a certain relation. There it's obviously important to really have a very big n and a very small delta n essentially to get a good approximation by the standard normal distribution. But it looks very encouraging in the kind of scenarios we have studied here. Okay, so this is kind of the main theoretical result, I would say here. And okay, so I wanted to just summarize. I don't want to show you lots of tables now, but if you're interested in these, please take a look at the preprint. I wanted to just summarize essentially our main findings. So we find that the proposed estimator for the Trawl function works really well in the finite sample studies we have considered in the simulation study. And I would like to point out that there's a lot of flexibility in modeling the Trawl function or the autocorrelation function. So I mentioned the exponential function to you, where we actually obviously have a very fast decay. But we can have truly long memory settings. So we can have essentially a polynomial decay. And we have also tried out the estimation in these settings. And in particular, when it comes to the consistency results, they still work really, really well. Also, Gaussianity is okay, but you need your big N and small delta N for these things to work nicely in the long memory case. Also, we would advise to use essentially a bias corrected version. You've seen that, maybe I could just briefly go back here. Sorry, that in the central limit theorem we had this derivative of the Trawl function appearing as soon as that mu term, the limit of n times delta n to the power 3, is not equal to 0. In practice, obviously, mu, in your finite sample study, the mu is never equal to 0. So you will always have this kind of error appearing. So if you just by default, even if in the limit the mu was equal to 0, if you were to account for that bias which can appear, then we find that this actually works quite well in our simulation study. So we would advise to work with the bias corrected version, and that's why this term appears here, even where theoretically you could say there is no asymptotic bias, but in the finite samples it's obviously showing up, and so it's good to do some bias correction here. Okay, and then also, as I mentioned, for the asymptotic Gaussianity, so if you want to construct your confidence intervals, you have to make sure that you check, how big the n is and that the delta n is essentially small enough. Okay, so now I wanted to show you, as a little illustration of this example, I wanted to show you an empirical study, and this uses the same data set which Mikkel Bennetson has kindly provided to us. So thank you, Mikkel, for that. So we are looking at high frequency data, bit-R spreads of one particular stock. So we're looking at the stock Agilent Technology. So it's a TKA, traded on the New York Stock Exchange, and it's measured in US dollar cents. We are looking at one day, the 4th of May, 2020. So we used the data from 10:30 to 4 p.m. So we discarded the first hour because there's a lot of activity in the market, and we are looking at the stationary process. Okay, so we don't claim that we can describe the non-stationary behavior with our Trawl process. So we use this kind of standard procedure which many people do when they do stationary modeling, that you are discarding essentially the opening time of the market. We use the standard cleaning method to just, clean for outliers and in the high frequency data. and then did a standard equidistant sampling. So we have now observations every 5 seconds using a previous tick method. And so when you're looking at this day, you have essentially 4,000 observations for the day. So this is the sample size we're dealing with the delta n being 5 seconds, okay? And then we are looking at the spread between the bid and the ask prices. So here the blue line is the bid price, the orange line is the ask price. And when you see when you just see how the prices behave, they obviously don't look stationary. But when you look at the difference between the two, and this is what's plotted here on in the second panel, then you see that this looks more stationary. Okay, and also when you test for stationary, that looks okay, right? But you also see that there is a lot going on at the start, and this is essentially the time period which we have discarded. Okay. And yeah, then we have estimated our Trawl function. So this is, first of all, this is just the autocorrelation function, the empirical autocorrelation function of the Trawl function, and of the Trawl process. And here on the right-hand side, the black dot is now the estimated Trawl function. Okay, remember this was our objective, to estimate that boundary of the fishing net. Okay. And so the black dots are the estimated points of that Trawl function, and then the blue dots give you essentially the 95% confidence intervals around this using the asymptotic theory we have looked at now just before. Okay, but this is all pointwise. Okay, for these individual points t. Okay, and then you might say, so what? Now I know my Trawl function. Can we do something with it? And then we thought, okay, we could maybe look at the forecasting exercise. One of my PhD students, Dan Leonte, he's working on Trawl processes as well, and he has derived a nice forecasting formula for Trawl processes, which essentially says that the conditional expectation of xt plus h given xt can be expressed as a linear combination, where you have a linear combination of xt, so the time point, time t, which we know, and the expectation of that Trawl series, and then there are two coefficients, and it turns out actually that you see this is the back measure of A intersection AH. So this formula is actually the covariance, the autocorrelation function of the Trawl process. And what you see here turns out to be 1 minus the autocorrelation function. And so now we thought, okay, let's try to use this as essentially for forecasting. I mean, ideally, you would use the conditional expectation given the entire history, right? Given FT. The Trawl processes are highly non-Markovian, okay? So conditioning on FT and conditioning on XT is not the same thing, but we use this as essentially as an approximation, and we see how well we can essentially predict based on that formula. And so we have our observations, say x0 up to xn minus 1 times delta n, and we want to predict, say, to time t plus h. And then we can derive this prediction formula where you see now we have to approximate these Lebesgue measures of A intersection with AH. And essentially these terms are just integrals, suitable integrals of the Trawl function. And because we have estimated the Trawl function, we can actually now just approximate these integrals using essentially Riemann sums, okay? And we prove the consistency of these as well. So I haven't shown you the results, but we prove that these are the correct estimators. And then we have essentially a nice forecasting formula. And okay, and now I just wanted to show you some results here. So when it comes to the Trawl process, we just wanted to have now some competing procedures, okay? So we want to predict up to here 20 steps ahead. And we, as competitors, we have the naive forecast where you just say tomorrow's value is today's value, okay? And then we have a parametric procedure where we are estimating a parametric model, parametric Trawl model, and we see how well that does essentially in the forecasting exercise. And we use essentially the model which we used in the paper with Mikkel Bennetson, where we find that a negative binomial distribution with some sort of long memory type Trawl works fairly well. And so we have fitted that model as well. And then, as we have seen in the forecasting formula, we can actually also just use the empirical autocorrelation function as the factors in the forecasting formula. So we use that as a competitor as well. And so these are the 3 methods we compare with our non-parametric forecasting formula. And then we are computing error measures. So we are computing mean square errors in the forecast, and we are computing mean absolute errors in the forecast. And then we are looking at the ratio between these two, between the error measures, between two different procedures. And then, because, you know, if they are the same, you would just get one. So we are subtracting one to have things centered around 0. And essentially what you get is, if you see a blue bar here, then that means that our predictor based on the non-parametric Trawl estimation is doing better. If you see a red bar, that means that the other model, the other procedure is essentially doing better. And so when we are comparing our method with the naive forecast, then we're essentially doing better. That's maybe not so surprising, or that's at least what you would hope you would get. And then when we compare here, so this is a comparison with the parametric procedure. Here we see it seems like the parametric procedure seems to win initially, but then for higher lags, the non-parametric one seems to be doing better. If you use the mean square error as your kind of loss function, if you use the mean absolute error as your loss function, you see that the non-parametric estimation of the model seems to work a bit better here when it comes to predictions. We also run the Diebold-Mariano test to test where the null is that we have equal forecasting performance versus the alternative that our method is the winner, essentially. And then we have, you know, the different stars for different levels of significance. But from my perspective, the main takeaway from this kind of analysis is more that, you know, the non-parametric estimation method actually is very simple to estimate. Okay, you don't have obviously the problem with, you know, first finding your parametric models, doing the model selection. And in some, you know, when you look at the higher legs, it does better than some of the competitors. But because it's so easy, I would say it's at least on par with the existing methods, but easier to choose, I would say, easier to implement. So that's, I think, a nice win for that particular methodology. Okay, and so let me just wrap up. So I hope that you find the class of Trawl processes interesting. So it's a broad class of stationary, infinitely divisible stochastic processes. They can account for short and long memory, so they are very flexible. And because you have, you know, the Levy basis and the Trawl, the fishing net, as the two modeling components, it turns out that you can model essentially the marginal distribution and the serial dependence completely independent of each other. And in some other, you know, like the Dharma models and so on, there was essentially a link between the marginal distribution and the memory, and that's not the case in the Trawl. So this gives you a very flexible way essentially of modeling. So that, I think, is very nice. So this work is now the first non-parametric estimation theory for the Trawl function. We proved the consistency of our estimator, and we also proved the feasible versions of the central limit theorems. Okay, so it's infeasible, but also the feasible one, which is the one you would be using in practice. The simulation results suggest that the final sample performance is pretty good for these methods, and so we can estimate both the Trawl function, but also integrals of the Trawl function with very high precision. Okay, and when it comes to our little forecasting estimation, our forecasting application, I would say that these non-parametric methods work at least as good as the existing methods based on parametric methods, but they are possibly slightly easier to implement and so on. So I think this is a very nice outcome. And if you want to have a look at some of the results, so we have the preprint on arXiv, and we have also the code on GitHub and on Grant. So thank you very much.
Thank you very much. We can stop the recording and then move to the informal chat.